Hi, welcome back to Educator.com. Today we're going to talk about an introduction to series. In the previous lesson, we introduced the idea of a sequence, that is, an ordered list of numbers. With this idea in mind, we can now discuss the concept of a series, summing up the terms of a sequence. Now, at first this might seem a little bit silly, right? It's just addition, and we've been doing addition since kindergarten, so why do we need to talk about addition in a special way? But consider how long it would take to add up 100 terms by hand. Could you imagine how much time it would take up if you had to add up 100 different things from a sequence? What if it were 1,000 terms or 10,000 terms? The study of series can make these seemingly colossal summation tasks, having to add up huge numbers of numbers, really, really easy. We can just turn this stuff into being some trivially easy task once we figure out how to talk about series in a deep way. Being able to easily add up lots of numbers has many applications. You'll see it in science, engineering, economics, computer programming, advanced math, and many other fields. All these things benefit greatly from the study of series, from being able to talk about adding up a whole bunch of numbers in an easy way where we can talk about it in compact notation. All of these things are really important to a variety of fields, so this is a great thing to study. Let's start off by defining a series. So given some sequence A1, A2, A3, A4, ... a series is the sum of the terms in the sequence. So it's just adding up the terms, or maybe a portion of them, maybe not the entire sequence, but it's just adding up terms from the sequence. If the sequence is infinite and we're adding up all of the terms from that sequence, we call it an infinite series. It adds all of the terms together. So that I'm saying it keeps going forever, right? It's A1 plus A2 plus A3 plus A4 going on forever. So plus A5, A6, A7, A8, blah, 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 forever and ever, right? Since our sequence was infinite, we're just saying keep adding them forever and ever. That's an infinite series. On the other hand, we can talk about a sequence that's not infinite, or if we only wish to add up a finite number of its terms, right? We aren't going to add up them forever, we're just adding up a portion of them, a finite portion of them, just a, number where we can count how many are there. We call this a finite series. Adding the first n terms of the sequence together is called the nth partial sum. So if we add A1 plus A2 plus A3 up until A1, but notice it just stops there, we don't go any farther past AN, then that is the nth partial sum because we're adding up all the terms 1, 2, 3 up until we get to n. So it's the nth partial sum because it's only a part of our infinite sequence. Consider if we had a sequence defined by the general term an equals n plus 2 to the n over 3 to the n. That is 1 plus 2 over 3, 2 plus 2 squared over 3 squared, 3 plus 2 cubed over 3 cubed, 4 plus 2 to the fourth over 3 to the fourth. What if we wanted to talk about its 30th partial sum? So in talking about its 30th partial sum, we'll see very quickly why we need a special form of notation for series. Why writing this stuff out by hand is going to be a real pain. So if we wanted to write this out, we'd have to first show the pattern that occurs here, right? We have this pattern that created each one of these various terms, so we'd have to have that show up in our summation. Otherwise, we wouldn't be able to realize what pattern's going on. So we're going to at least need the first 3 terms at least. Then we could use an ellipsis, that ... to say that the pattern continues on in this manner. So we can not have to write a massive amount because we can use the ellipsis to say the pattern keeps going, but we're still going to have to show it stop at the 30th term. So at a very minimum, we're going to have to write out the first 3 terms, the last term, and an ellipsis in the middle. So we'd have to write out 1 plus 2 over 3, plus 2 plus 2 squared over 3 squared, plus 3 plus 2 cubed over 3 cubed, plus ... plus 30 plus 2 to the 30th over 3 to the 30th, right? That's the 30th partial sum like we were talking about. But that's a lot of stuff to write out, right? Yikes! That's a lot of writing for a fairly simple series. This isn't even that complicated, but if we had to write this on multiple lines, right, as we worked through a problem, if we had to keep talking about this over and over as we did steps in a problem, your wrist is going to hurt after doing one of these problems. You're going to have to do a bunch of problems about summation. So this is why we need some sort of notation. We need notation to make it easier to compactly describe a series. We don't have to write out this really, really long thing every one time we want to talk about some summation from a sequence. We need some easy way to be able to do it in a short way. Enter sigma notation. To compactly describe sums, we use something called sigma notation, also sometimes called summation notation. Why is it called sigma notation? Because it uses the uppercase Greek letter sigma. So sigma is this guy right here. If you're drawing it by hand, this is a computer-drawn picture of sigma, right, made by a computer typesetting program. So if you're drawing it by hand, I would recommend writing it like this, right, where you've got these little hooks, right, these sort of little vertical hooks on either end, and then it's just kind of a capital M on its side, right? Just write it out like that, and that's great. If you're feeling lazy, you can wind up just sort of writing it like that as well, but it helps to write it like this so we can clearly see what it is. But if you're doing a lot of problems that way, don't worry if it winds up getting not quite absolutely perfect each time, because you'll be able to recognize it from other things that are about to be seen. All right, so let's see how we use sigma notation. Let's look at the anatomy of a series in sigma notation. So the first thing to look at is the thing being summed. The terms from the sequence given by AI, so this thing to the right of the sigma, are added together. This is what will be added together over and over with each step as we add up the first thing and then the second thing and then the third thing and so on. It might be a sequence, but it's much more often going to be an algebraic expression, something like 3 times I plus 10, or 2 to the I, or I factorial, some so that we could plug in a number and be able to churn out a value. So you'll often see algebraic expressions, but once in a while you will see a sequence like A sub I. Next, the index of summation. So I is the index. It increases by 1 for each step of summation, right? We do the first thing, then we add the second thing in the next step, then we add the next thing in the next step, then we add the next thing in the next step, and so on and so forth. So every time we step forward, the index will click up by 1. So we start at some value and then we go the value 1 above that, then the value 1 above that, then the value 1 above that, and so on. So every step it will increase by 1. The index can be any symbol, but I is very common, and that's what we'll wind up using for the most part in this course. So that's the thing that winds up changing, and notice how I will generally occur over here in the series as well. That's saying this is the thing that changes, this is what will change with each step, this little guy right here. The lower limit of summation. This is the first value used for the index. This is where the series starts. So in this case, since I equals 1, our first value would be plugging in a 1 for the I. The upper limit of summation, this is the last value used for the index where the series ends. So we would step up until we eventually got to some value n. All right, let's see it in action. So we've got this pictorial summary of how it works. This is a great picture, so check against this if you get confused at a later point. This is a great slide right here. Let's see it in action. So we've got sigma, it's I equals 3 for the starting index, and then 7 is the upper limit, and we've got 2I minus 1 as the actual expression. So the very first thing, we've got the I right here. We start at I equals 3. So the first value that we plug in for our I is 2 times 3, right? Because our lower limit of summation was that 3. So 2 times 3 minus 1. That's the first thing. Then we go on to our next step. Plus, we increase our index by 1. Our index is started at 3, so it goes 3 plus 1 to 4. So 2 times 4 minus 1. Then we go on to our next step. So it'll be 2 times, we were at 4 in the last step, so it increases to 5. So we're new at 4 plus 1, 5. So 2 times 5 minus 1. Plus, our index increases by 1 again, so 2 times 6 minus 1, plus, and now finally we are just hit our final, the upper limit. So at this point we stop. This will be the last one. Once we click up to this this final upper limit for how high our index goes to, that is the last one in the series, so 2 times 7 minus 1. And at this point we could simplify it out if we wanted, right? We could get a value from this, but that's also a good way to see how it expands, and that's all we're looking for right now, seeing how it expands. But if you wanted to, you could simplify each one of these, and you could also combine them and be able to get a value for that series. So far, we've only seen how to use sigma notation for finite sums, that is to say partial sums, not sums that are going on forever. Since they've all had some upper limit of summation, right, something on top of the sigma, they've all had to eventually stop, right? They've had some top limit to how far they step out. If we want to show an infinite series, one where the series, the terms, they keep adding forever and ever, we simply put an infinity symbol on top of the sigma. This shows that the series has no upper limit and instead continues on forever. So if we had a sigma with I equals 1 as on the bottom, right, our index is I, our lower limit is 1, and our upper limit is infinity, that says really just keep going. It's not that we actually get to infinity and stop. We can't ever get to infinity. Infinity is just the idea of going on forever. So we start at 1 and then plus, and then on the 2, and then on the 3, and then on a 4, and then on a 5, and then on a 6, and it just keeps going forever and ever. So we'd have, since it's a sub I, we'd have a1 first because it was a 1 for our lower limit, then a2, and then plus a3, and then plus a4, and then plus a5, and it will just keep going on forever because it is an infinite series that we're working with. If we wanted to see it in specific, here's an example that uses specific numbers. So we've got some series with I equals 1 on the bottom. It's an infinite series because of the infinity on top. So we have 1 over 2 to the I. So our first I is 1. So that's 1 over 2 plus 1 over, so 1 over 2 is our first term, 1/2, plus 1 over 2, our next step of the I will be now at a 2. So 1 over 2 to the 2, 1 over 4. And then our next step would be I at 3, so 1 over 2 to the 3, that's 8. Then our next step I will be at 4, so that's 1 over 2 to the 4th, so 1 over 16. And then I will be at 5, so it's 1 over 2 to the 5th, so we'll have 1 over 32. And that pattern will just keep going. We'll keep adding them on forever and ever. Sometimes it's useful to re-index a series, or a sequence sometimes. We might have a series that has the index begin at one value, but we want it to start at another value. For example, we might want a transformation like this one here, where we have in our original sequence, I equals 7 as our starting index, and it's got some upper limit, and it's got some expression that we're actually working with. And we want to transform it to k equals 1. We want our starting index to be k equals 1. And we're going to, of course, need also some upper limit and something here. Now, of course, we can't just change the number of the lower limit. If we just went and changed the lower limit, that would affect the whole series. So we have to pay attention to how does the thing being summed and how does our upper limit, how will they wind up making the transformation as well? They're going to change over the process. They're not going to be the same thing on the left side and the right side. They're going to wind up becoming different things. Otherwise, we would have altered the whole thing by starting, if we start at one starting place and then we just change the starting place and we don't do anything else, well, you start at a different starting place, you're going to have different values coming out. So since we want to wind up having the same value come out of our two ways of talking about it, we have to alter every part of the sigma notation so that we can get the index we want without changing the value that comes out of it. You're probably asking, why do we care? If we've got it written in one way, why not leave it that way? Well, there's a bunch of reasons to do it. For example, if you're working on a proof, it can sometimes help to reindex it. But specifically at this course, a lot of formulas that we wind up working with will be given in the form of something with an I equals 1 on the bottom. So since a lot of our formulas will have I equals 1 on the bottom, we'll have to start at this index of something equals 1, some symbol equals 1 to be able to work with some of the formulas we have. A lot of the formulas you wind up seeing are in this format, so it's really helpful to be able to reindex so we can get to a format that we already have a formula for, as opposed to having to figure out an entirely new formula for some new different index. Right. So how do we actually reindex? The most essential way is to expand the sigma notation into a written out series, then see how we could rewrite the pattern with our chosen starting index in mind. So for example, if we want to go from I equals 7 to k equals 1, we can just start off by, a series is just a shorthand way of writing out something plus something plus something dot 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 plus something, right? And even that's a shorthand way of writing out every single term. So we can expand it into that format. So if it's I equals 7 first, then we'd have 3 times 7 minus 16. Next thing would be plus 3 times one step up to 8 minus 16. Plus, it'll continue in this form, and 3 times our final upper limit is 22, so 3 times 22 minus 16. Great. So if we want, we could figure out how to write this sigma over here with just that in mind, but we can also simplify things first, see if we can see another easier to see pattern. So 3 times 7 would get us 21 minus 16, plus 3 times 8, 16, 24 minus 16, plus dot dot dot, plus 3 times 22, 66 minus 16. So 21 minus 16, that's 5, plus 24 minus 16, that's 8, plus dot dot dot, plus 66 minus 16, that's 50. So we look at this and we might realize, oh, what it's doing is it's going up by 3 each time. And that makes sense since we started at 3i. So it's going up at 3 each time. So if that's the case and we want to get this k equals 1, then that means that we know here we're at k equals 1, here we're at k equals 2, here we're at k equals, we'll actually leave that as a question mark right now because we don't quite know yet. We'll talk about that in just a moment. What number we're at. Well, let's see why. So k equals 1, if it's plus 3 each time, we're going to want some 3k plus some number. So if we're 5 here, then that'd be 3k plus 2, because 1 for k, 3 times 1 plus 2 does get us 5, so that checks out. Here, would 3k plus 2 work as well? So 3k plus 2 here, we plug in 2, 3 times 2, 6 plus 2, 8. Hey, that checks out as well. So it looks like it's going to be some 3k plus 2 will be here, so we'll have 3k plus 2 for that part right there. Now, what's the upper limit of summation going to wind up being? Well, if we're at 3k plus 2 and it equals 50, we have to figure out what value would wind up coming out here. So k equals question mark. We could solve for this. 3k equals 48. K divided by 3 now on both sides, we get 16. So we know our upper limit is going to have to be 16. Another way of doing it is to notice what's the difference between our upper limit and our lower limit. So in our original, we had 22 as our upper, 7 as our lower. So 22 minus 7 means 15. Oh, whoops, sorry, not 15. 22, oh, sorry, it is 15, my bad. So 22 minus 7, that comes out to be 15. So over here, we know that we're going to have to wind up having that difference of 15 as well, since we start at k equals 1. K equals 1, so 1 plus that same 15, because we're going to have the same number of steps, however we phrase it. So 1 plus 15 comes out to be 16, which is the same thing we figured out it has to be to work there. So with that in mind, we now know our lower limit with our index is going to be k equals 1, because that's what we wanted to figure out in the first place. Our upper limit of summation will be 16. We figured out 2 different ways that has to be the case, because 16 minus 1 is 15, which is the same as 22 minus 17, or alternately we can solve for it using the formation we came up for that general term, and then 3k plus 2 is what's actually going in that's being added on each term. And so that's one way of doing it. We worked this out by expanding first. Expanding is a very specific way to see it. It's a great thing to do if you get confused by the problem you're working on. There's another way to do this, though. We can also reindex by thinking in terms of substitution. How do our old index and the new index we are creating relate to each other? We can think in terms of substitution. So consider, once again, if we wanted to convert from I equals 7 with all the same thing to k equals 1. Well, since we've got I equals 7 and k equals 1 both at their starting places, how is I related to k? Well, I is the same thing as k plus 6, right? 1 plus 6 gives us 7. So we've now got this relationship of I is equal to k plus 6. And with this in mind, we can substitute to figure out what the upper limit is, and then to figure out what the general term is. So to figure out the upper limit, we know I equals 22 is what we're going to plug in, since that's its upper limit, right? And then we're going to, over here, we know I equals k plus 6. So I equals k plus 6. So we plug in 22 for I. So we have 22 equals k plus 6. Subtract by 6 on both sides. And we get 16 equals k for its upper limit. All right. So at this point, we can now write our sigma is going to wind up being upper limit of 16. The lower starting index at k equals 1. Now, what is it going to wind up being? Well, here it was 3i minus 16. So we've got 3. What is our I in terms of k? Well, I is k plus 6. And then we continue on with the rest of it, minus 16. So we've substituted out the I here for the k plus 6 here into what I was in our initial version for the sigma notation. So at this point, we can expand this and work this out, simplify it if we want. We could also just leave it as it is, and it would be just fine. So the upper limit and lower limit, our index, they'll all stay the same throughout. So we work this out. 3 times k plus 6 gets us 3k, plus 3 times 6 is 18, minus 16. And so we get 16 for our upper limit, k equals 1 for our index and lower limit. 3k plus 18 simplifies to 3k plus 2, which is exactly what we had the first time. Cool, when we did this through expanding it. So substitution, expanding, they both work the same way. Substitution is probably a little bit faster and easier, but it's a little bit more complicated to see what's going on to really understand. The important thing is figure out how is your I and whatever your initial symbol and the new symbol that you're changing to, how are they related to each other? And you probably start with the lower limit, and then what will your upper limit have to be to have that same relationship between old index and new index? And then what is your expression going to wind up being if you just plug in your connection between the two indexes? Cool. All right, working with series, there are various properties we can occasionally use to our advantage. So let's look at some properties of sums. Below, let AI, BI, they'll be sequences. So they're things that are allowed to change, but C will simply always be a constant. Our first one is that the sum from I equals 1 to n of C is equal to C times n. Remember, C is just a constant. So why is this the case? Well, remember, if we had the sum of I equals 1 to n of C, well, C doesn't change any time because it's a constant. It isn't affected by the index. So it's just going to be C plus C dot 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 plus C, right, that many times. So if we've got that, how many times did it show up? Well, we went from I equals 1 up until n, so 1, 2, 3, 4, we count up to n. Well, we've got a total of n terms in there. So if C adds to itself n times, then that's just C times n. So that's equal to C times n, and that's where we get that property for how sums work. So if it's just a constant being added through a series, we can just multiply it by the number of terms in that series. Next up, we've got the summation of some summation, and this will wind up working for any summation limit. So the only thing we have to care about is the index. You can start with any lower limit, any upper limit, including an infinite sum. It's still going to wind up working out the same. So C times AI, we can do this where we pull out the constant and we bring it out to the front, and it's C times the summation of AI. So why is this the case? Well, notice, our first term would be C times A1, plus our next term would be C times A2. Plus our next term would be C times A3, and it's going to continue on in this pattern. It might end, it might not end, so we'll just leave it as dots there. But notice we've got a C on each one of our terms. So if we want, since we've got a C here, a C here, a C here, and that thing is going to wind up continuing, right? There's going to be a C on each one of these because we see it's C times AI. We can pull out all the C's, right? We pull them out, so it's C times A1 plus A2 plus A3 plus dot dot dot. So it's C multiplied against that entire series. It's not going to have any difference how we do it. So this entire series here to here, we can think of it as C times a new series of just the AI's changing, and that's how we wind up getting the same thing here. Final idea, if we've got addition, AI plus BI, well, we can wind up breaking that into two separate series added together. And once again, this will wind up working with any limit, so that's why we don't have a lower limit, don't have an upper limit, just an index, is because this will work with any limits whatsoever, even in infinite series. So we could write this, if it's series of AI plus BI, well, that's going to be A1 plus B1 plus A2 plus B2 plus A3 plus B3. And it's just going to continue on in that format. Well, addition, order of addition doesn't matter, right? A1 plus B1 plus A2 plus B2 is the same thing as A1 plus A2, then plus B1 plus B2. So what we do is we'll order all of our A1s first. So we'll have all of the A1s in our series show up first. And then we'll add on our B1s. B1 plus B2 plus B3. And that will also go on the same as it would have on its own. So at that point, what we've done is we've just reordered how we are looking at the series, since we've expanded it and now we've reordered the way we're looking at it, but we haven't changed anything. So at this point, we can just pull it into two separate series, I. So we'll have AI here plus, and then the BI, right? There's the A portion of the series and the B portion of the series. So we can either have them intermixed together, or we can spread them apart and work on each of them on their own. And that's how we wind up having this final property. All right, we're ready for some examples. First example here, given the sequence below, find the third partial sum. So if we're going to find the third partial sum, that's as easy as just adding up the first three terms. So that's 0, 3, and 8. 0 plus 3 plus 8. We wind up getting 11. Done. Easy peasy. Next one, if we're looking for the seventh partial sum, well, so far we only have 0, 3, 8, 15, 24, so we're going to have to figure out what will the pattern continue on to. So our first step is to figure out how does this pattern wind up working. We look at this through addition, 0 to 3, 3 to 8, 8 to 15. Well, the addition's changing each time, so we could think in terms of some recursive relationship. That's not really going to make it easier. Multiplication? Multiplication doesn't really work either. But we look at this for a while and might realize, oh hey, this looks kind of like 1, 4, 9, 16, 25, right? 0, 3, 8, 15, 24, that's just minus 1 on each one of the terms. So we can think of this as being, in general, n squared minus 1. So if that's the case, then we can figure out what are the next terms. If it's n squared minus 1, the next term to follow is going to wind up being 36 minus 1, right, because we're at 5 here. 5 squared minus 1 is 24. So the next will be 6 squared minus 1. That's going to get us 35. Next will be 7 squared minus 1. 7 squared minus 1, 49 minus 1, or 48. So at this point, the seventh partial sum will be adding up these first 7 terms. So 0 plus 3 plus 8 plus 15 plus 24 plus 35 plus 38. We toss that all into a calculator, and we wind up getting 133. There we go. All right. Next one, expand the below sigma notation into a series of terms added together using an ellipsis. So we break it apart into the thing where we're not using sigma notation, we're just writing it as one term after another with some pattern occurring. So what would our very first term be? Our very first term would start at I equals 3, so we plug in a 3 for our I first, so that would be 3 factorial over 7 to the 3. Plus, our next term would wind up being, we click up 1, so from 3 to 4. So that will be 4 factorial over 7 to the 4. Plus, our next one, we click up another one to 5 factorial over 7 to the 5th, plus dot, 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 plus. And we're going to wind up finishing up here at 15. We could also start off with something before 15. For example, we could write out 14 factorial, because that would be in the expansion. 7 to the 14 plus 15 factorial over 7 to the 15. So there we go. We've managed to write the whole thing out using ellipsis. We've expanded the sigma notation into a series of terms. And we don't have to necessarily write out all of these. We could probably get away with not writing, we could certainly get away with not writing this guy right here, the 14 factorial over 7 to the 14. And we might even be able to get away with not writing the 5 factorial over 7 to the 5th. Helps us see the pattern, but not absolutely necessary. But by including more terms, sometimes the reason we want to expand things is so we can manipulate how the terms work. So sometimes it's useful to include more things at the start and the end so that we can wind up seeing how things are interacting. It'll sometimes allow things to work out better. And we'll see that sometimes when we're working in proofs. Example 3. Condense the sum below into a series expressed using sigma notation. Notice it is an infinite series. So first thing is, let's notice, how do these connect to each other? How do we get 1/2 minus a quarter plus an eighth minus a 16th? Well, we can break this into a sequence first that just has a series going on. So let's look at this underlying sequence. How do we get from 1/2 to negative a quarter? Well, we multiply by negative 1/2. How do we get from negative 1/4 to positive 1/8? We multiply by negative 1/2. How do we get to the next one? We multiply by negative 1/2. So with this in mind, how can we create a general term an? So that's going to be an is equal to, since we're multiplying by negative 1/2 each time, so it'll be negative 1/2 to the, is it going to be to the n? Well, here we're going to wind up starting with something else actually. So n minus 1, because here's n equals 1. We want to not have anything at the beginning, which we could write as times 1/2. So negative 1/2 to the n minus 1 times 1/2. Alternatively, another equivalent way to write this out, we could write this as negative 1 to the n minus 1 over 2 to the n minus 1 times 1 over 2. So the 2's in the denominator will wind up compacting together. And we could also write this as negative 1 to the n minus 1 over 2 to the n. Right? Both of these, just fine ways to write it. We'll wind up getting the same thing. Whether we write it using this general term or we wind up writing it with this general term, we'll wind up getting the same series. What is our first term? We decided to set it at some n equals 1. Let's use an index of I, just because that's what we're used to. Although we could use n. Sometimes we might have a little bit of confusion since we're used to talking about nth terms with n, so it might be weird to use an index of n, but you'll often see it used as well. I like I, so I'm going to use I. I equals 1, because that's our first location. What do we go up to? Well, it's an infinite series because it goes on forever. We're never told it stops. So we use an infinity symbol on top. And then let's do this one first. So we could write this as -1/2 to the n minus 1 times 1/2. And that whole thing has the series applied to it. Or equivalently, this would also be equal to the series, same upper limit of going on forever and same starting index. We could also write this as -1 to the n minus 1 over 2 to the n. Either way, we wind up working it out. Both of these are just fine. They're going to give us the exact same answer. They're just two different ways to write it out. Depending on the specific problem, might be useful to write it one way or the other, but any teacher, if this was just the question, should accept both of these. All right. Calculate the value of sigma with a lower limit of 0, upper limit of 4. V is our index, where the expression is v factorial minus 5v. So the first thing we do is we plug in v equals 0 for our first 0. So our very first term is going to be 0 factorial minus 5 times 0, right? Our index is v, so that's the thing being swapped out. Plus, we step up our index to the next level, 0 up to 1 now. So 1 factorial minus 5 times 1. Plus, next thing stepping up from 1 is 2. So 2 factorial minus 5 times 2. Plus, next thing from 2 to 3, 3 factorial minus 5 times 3. And then plus 3 to 4, 4 factorial minus 5 times 4. Finally, at this point, we notice, that's our upper limit, so we stop, right? We step from our lower limit, 0, 1, 2, 3, 4, upper limit, so that's where we stop, and we do each of the steps in between, add them all together. So now it's just a matter of simplifying to actually get the value. What is 0 factorial? Remember, 0 factorial is simply defined to be equal to 1. All the other numbers factorial is that number times each of the numbers underneath it, all the integer numbers underneath it, positive integer number underneath it, but 0 factorial is just simply defined to be 1. So 0 factorial gets us 1, minus 5 times 0 is 0, plus 1 factorial is just 1 times itself, so 1 minus 5 times 1, 5, plus 2 factorial, 2 times 1, so 2 minus 5 times 2, 10, plus 3 factorial, 3 times 2, 3 times 2 times 1, so 6, minus 5 times 3, 15, plus 4 factorial, 4 times 3 times 2 times 1, 24, minus 5 times 4, 20. We work this out, so we've got 1 here plus -4 plus -8 plus -9 plus +4. We see that we've got a +4 here and a -4 here. They cancel out. 1 plus -9 gets us -8, so we've got -8 and -8, or -16 once we simplify the whole thing out. Great. Fifth example, reindex the series below so it starts at the index k equals 1. So we're looking to swap the index I equals 5 out for k equals 1, but have the exact same value come out of the series, right? Our sigma notation will change, the upper limit will wind up changing, and the expression here will wind up changing to some extent so that we can achieve this without affecting the value of the series. So we talked about two different ways to do this when we went through the lesson. The first way we'll approach this is through expanding it. So we'll start off by doing it through expanding it, and then later we'll look at doing it through substitution. So two alternative ways, whichever one makes more sense to you, that's the one you probably want to wind up using for your own work. All right, so we want to start off by expanding this. So if we're going to expand I equals 5, 3 to the 7 minus I, so that's going to be, our first thing would be 3 to the 7 minus 5, so 3 to the 2. Plus, and then the next would be 6 for our I, so 3 to the 6 minus, 3 to the 7 minus 6, so that'll be 3 to the 1, plus, then at 7 we'll have 3 to the 0, plus, plus, and then finally when we get up to an upper limit of 20, 7 minus 20, -13, so it'll be 3 to the -13. Okay, so that's what we see we wind up getting out of this. 3 squared plus 3 to the 1 plus 3 to the 0, to 3 to the -13. So we see that the top steps down 1 each time. So we wanted to figure out how can we wind up showing this. So we start with k equals 1 for this first slot. And here's k equals 2, k equals 3, and here's k equals don't know what yet. We can actually figure out that it's going to have to be 20 minus 5 is 15. So 1, our starting lower limit here, 1 plus 15 would be 16. We know it will wind up having it come out to 16, but let's work through it the other way. So what we've got here, it looks like we could write this as 3 to the 3 minus k. Right? 3 to the 3 minus 1 would get us 3 squared. The next one, 3 to the 3 minus 2, would get us 3 to the 1. Hey, that works out. At k equals 3 on our third term, we'd have 3 to the 3 minus 3 would be 3 to the 0. Hey, that winds up working out. So if we're going to have 3 to the negative 13 equals 3 to the 3 minus some k, then we're now going to know negative 13 has to be equal to 3 minus k. So we've got k equals 16 as our upper limit as well. Great. So that winds up making sense. We can also figure it out once again from our starting upper limit was 20, our starting lower limit was 5, so that means there's a difference of 15. So if we have k equals 1, then 1 plus 15 has got to come out to be 16 as well. So that's going to be our upper limit. Two ways of looking at it. Either way, just make sure you're careful with this sort of thing. It's easy to get confused the first few times you work with it. So now we know what our general term is. It's 3 to the 3 minus k. We know what our upper limit is, and we know what our starting what our index and starting term is, lower limit. So we can write the whole thing out. So we've got 16 as our upper limit, k equals lower limit of 1, 3 to the 3 minus k. Great. So that is our answer, and that's doing it through expanding as our method. Alternatively, we could do this through substitution. We could have also set this up by noticing, well, we've got I equals 5 here, and we want to start at k equals 1. So at the first place, we have I equals 5. And then at our second place, we have k equals 1. So if we have I equals 5 here and k equals 1 here, then we can see that I is equal to k plus 4. So if I is equal to k plus 4 in general, right, this is just going to hold true in general, then what about our upper limit? Our upper limit is going to have to wind up being the case that when I is equal to 20, what will our k wind up being? So we'll have 20 equals k plus 4, which means 16 is equal to k for the upper limit. So 16 equals k for our upper limit. Now we just plug in through substitution. So 16 is our upper limit. We just figured that out. K equals 1 is our index and lower limit. So it's going to be the same thing we started with, 3 to the 7 minus I. So 3 to the 7 minus, but we're not going to use I, we're going to use I equals k plus 4, right? So we're going to swap out this I here for k plus 4. So we substitute that in, and we've got k plus 4. We can now work this out and simplify it since it's the upper limit and lower limit and index. None of those will change. We're just simplifying what's on the inside. So 3 to the 7 minus quantity k plus 4, so minus k and minus 4. 7 minus 4 gets us 3, and minus k gets us 3 minus k in the whole. So we wind up getting the exact same thing. Either way, we wind up approaching this through substitution or through expanding. We can wind up re-indexing the series so we can have it change at a different starting index. They both work fine. Whichever one makes more sense to you, that's the one I'd recommend using. All right, final example, calculate the value of the series below. Use summation properties to make the math less tedious. So we could just do this by hand, right? We could go, all right, so we've got 3 times 1 minus 5 plus blah, 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 plus all the way up to 3 times 15 minus 5. Okay, and then we could calculate what is 3 times 1 minus 5, then what is 3 times 2 minus 5, then what's 3 times 3 minus 5. And we can do this by hand or through the calculator, but that's kind of a pain, right? That's going to be a lot of writing. It's going to be a lot of calculation. Luckily, there are some clever ways to use the summation properties that we learned earlier to make this at least not easy, but less, not fast, it'll be easy, but less tedious, so we have to do less writing. So how can we do this? Well, first off, remember, we can split based on addition. So we can see this as 3i plus negative 5. So 3i plus negative 5, and we can split this into I equals 1. The limits to our summation will never wind up changing, but we can split this into a 3i plus, same sum over here, 15i equals 1 on negative 5. Cool. We were allowed to pull out constants, right? So we've got this constant of a 3 here. We've got this constant of a negative 1 here, effectively. So we can pull those out front. So we can now write this as 3 times the summation of 15 I equals 1 of I plus, plus -1, so let's just write that as minus summation 15 I equals -1, positive 1, got confused by the negative, on 5. Great. So 3 times, well, there's no cool properties that we've learned yet, although we will learn in the very next lesson how to easily sum this one up. But we'd have 1 plus 2 plus 3 plus ... plus 15. And over here we'll have minus, well, we could do 5 plus 5 plus 5, but it's just going to show up 15 times, right? We have I equals 1 to 15. We talked about this before. Since a constant's just showing up 15 times, that's just going to be 15 times the constant. So it will be 15, the number of terms are there, times the constant that's showing up over and over, so 15 times 5. So we can now work out with a calculator 1 plus 2 plus 3 plus blah, 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 up until 15. That winds up working out to 120. So we've got 3 times 120 minus 15 times 5, 75. 3 times 120 is 360 minus 75. That comes out to equal 285, and there's our answer. So we still had to do a little bit of writing this out, right? The slowest part here is going to be adding by hand 1 plus 2 plus 3 plus ... up to 15. Or by using a calculator. But either way, that's way better than having to multiply numbers and then subtract 5 and then add that each time over and over. So we can use these summation properties to split things up into ways that make them easier to work with. All right, cool. In the next lesson, we'll wind up looking at our first specific kind of sequence in series, arithmetic, and then later on we'll work at geometric, which will let us apply these ideas about series into one specific thing where we can actually start creating some formulas to make things really easy and fast. All right, we'll see you at Educator.com later. Bye.